Oh, little Flo, I love you so, especially in your nightie. When the moonlight flits across your tits, oh Jesus Christ almighty. Greetings, the Astro 30 here, and today's video is a little bit different. I'm planning on making a series of videos of going from a design concept to a finished product. In this video, we're going to be designing a relatively simple but versatile DC speaker protector circuit. It's probably the most simplest circuit that we can come up with. But that's the premise of these videos, is to take it from design concept into a full finished product. In this case being a etched PCB populated with components. And I hope that this series of videos will be interesting to some people. Now, for a speaker protector, what we need to do first is, before any preliminary design of drawing out schematics and stuff, is to work out what we actually need. So we need a functional block diagram. So we're going to start with the simple. I'm going to start here with a box, and we're going to call that DC DET, which is short for detect. And you'd have your inputs from your amplifier. You could have several channels, like it could be a 2.1, 5.1, 7.1. We just have separate inputs for each channel. We are also going to need a relay driver, and that will consist of all our relays, and we'd have a bunch of outputs to the separate speakers. We're also going to need a loss of AC detector. So when the power switch at the front of the unit, for instance, that this is in, is turned off, the relays drop out instantly. We'll call this line here the off line, because everything is relative to it. And we're also probably going to want some form of indicator, so we'll just draw it like that. So indication, so that we know that when it's in protect mode, we don't want the, like for instance an LED, we don't want the LED to be on when the relays are engaged. We want the LED to be on when the relays are off, telling us that the unit is in protect mode. So that's our basic block diagram of what we need. So what we need to do is we need to start from the beginning, which would be a good idea. But we'll start with this section here, the DC detector, because we want to work out what we need in there, and we're going to do that little bit of circuit first and test that on its own. And everything is going to be done on breadboard, hence the breadboard here. And that's always a good idea, to always breadboard circuits when you're designing them. So in case you've got to change, we don't have to keep unsoldering and soldering components, which A, stresses the components, and B, stresses the material that it's soldered to. Also, it's a thorough pain in the ass if you've already etched the PCB and find half your traces are wrong, which means you've got to remake the thing again. So it's always a good idea to test and retest stuff on a breadboard first. So anyway, let's have a look at this DC detector. Okay, so I've got the DC detector all drawn out. It looks overly complicated than it really is. It's relatively simple in operation. Now, there's one thing to note here. This is designed for bipolar supplies only. In other words, the amplifier must be a bipolar amplifier with a plus, a minus and a 0 volt rail. and we're using the DC plus VCC and DC minus off of the filter caps of the power supply that the amplifier is using. Now, starting from the front, we've got a left input, a right input, and an auxiliary input. Now you can add extra A lines into these points. That's why there's dotted lines here, meaning that it's optional, you don't have to have it, and you just add this front end part multiple times to give you more inputs, all connected to the same points. But I've just drawn this in here for reference. So up here we have a 100K and a 100 microfarad, and this is a bipolar capacitor, it's not an electrolytic. About 50 volt, and what this is a filter. It filters out any AC signal on the line so that it doesn't false trigger the detector, because even AC with low base frequencies of, you know, anywhere between 3 and 20 Hertz can look like DC to the transistors. Now we're going through two diodes here back to back. As we all know how a diode works, this diode, and they're all 1N4148s or 1N914s, this diode will only allow positive voltage to go in that direction, and this diode will only allow negative DC voltage to go in that direction. As we see here, we've got two transistors, a BC549 and a BC559, and their emitters are joined together. And basically, when a positive going DC signal is coming in, it'll go into the base of the 549 and turn it on. And when it turns it on, it allows current to flow through this circuit here. I will get to how it does through this transistor when there's no DC voltage present here in a minute. Conversely, the negative voltage comes through in here and goes to the base of this 559 PNP transistor. Now, down here you'll notice two diodes going to earth. One with the anode going to earth, one with the cathode going to earth. The cathode here on this one joins to the cathode of here, here, and here, and also to the base of the 549. Conversely, this one's anode joins to the anode here, 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 and to the base of this PNP transistor. What these two diodes are doing are basically slightly forward biasing these two transistors so they're slightly turned on. And when you get the DC voltage, either positive or negative, coming through these two diodes respectively, turning each one of these on hard will allow a larger current flow through the collector emitter collector junction, which then goes into this transistor. Now, this transistor under normal operation should be turned off or biased off. It'll only get biased on when there's enough current flow through these two transistors to turn this transistor on, which is why we've got a 15K resistor here to, you know, because these are slightly forward biased, we don't want the forward bias voltage and leakage current through here to turn this transistor on. Now, when this transistor turns on, that will bring, well, in this case, the negative voltage rail up through the collector emitter junction into our offline. I've also written a note down here, designed for Class B or AB amplifiers only. You wouldn't use it for a Class A amplifier, and you wouldn't use it for a Class D amplifier. Class A amplifiers have an output capacitor on them, and there should not be any DC ever present on its output, or very little. So that's the basic DC detector. Now what we're going to do is I'm going to build this circuit up on the breadboard, and we're going to test it, and we're going to look at what happens on this offline on a multimeter when we have DC present between one of these inputs and ground, either positive or negative. So let's get that all set up and ready to go. For people that can't get hold of the Fairchild type style transistors here, you could probably substitute them for 2N3904 and 2N3906 respectively, but that again is up to testing. The actual maximum voltage you can have across this circuit I would say I wouldn't push it plus minus more than about 46 volt, but you can always check the ratings of these transistors. If we were to use the 4.7, it would be a lower voltage. That's why we're using the 4.9 and 5.9 respectively, because they allow up to, I think it's 80 volt between the collector and emitter junction. So we should at least be able to get up to plus minus 40 volt, thereabout. Anyhow, that's detracting from what we're doing. My power supply only goes up to 30 volt, so we're just going to work with 30 volt. Okay, I've got the DC detector hooked up. I've only just got basically the left and right input channels filtering done. I didn't bother adding the auxiliary, but it's still the same premise. Before the end of this video I'll add an extra channel there, just, you know, to prove the point that you can have multiple channels hooked up across the same circuit. Now I've also got the DC power supply hooked up to it, plus minus 0. It's currently sitting at 20.7 volt for a test voltage for now. These wires flying off here in the background, there are audio inputs. The whites are the inputs, left and right, and the blue is the 0 volt rail for that. Got the multimeter set on the volt scale, hooked to that 10 ohm resistor. The original circuit was 4 ohm 7, but I don't have any, so 10 ohm will have to do, which is coming off the collector of this transistor here, which is our basically off driver, if you want to call it that. So I'll turn the load on, and not much should really happen on the meter, because, and it doesn't, because I've got this meter referenced to the earth, not to the negative rail, so we should only see, well, we're currently getting about 10 millivolt, so if I put that on the millivolt scale, actually it's a lot higher than I thought. It's about, when it finishes, it's gone off scale. Anyhow, so let's get our trusty 9 volt battery, and I'll hook it across the input of one of these channels here, and we'll see what the output of that transistor does. Currently nothing, so let's try the other channel. Okay, so maybe I need to reference that to the negative, so I'll reference that to the negative just to make sure I'm not going crazy. Yeah, that doesn't appear to be doing anything. I could have it incorrectly wired. That's always a possibility. So I'm going to have to do some investigation and see what I've done wrong here. Okay, in my haste to get things done, I forgot to connect these two diodes that go to earth back to back here to the bases of these two transistors, so they weren't even being forward biased, which could be a problem. We also need part of the RC, well actually the RC delay for the relay driver section connected, at least the resistor, but I put the capacitor in there to make the readings on the meter more easier to see. So basically all we've got at the moment is my penis. I've lost my pen. So basically what we've got now is a 10 ohm resistor instead of the 4R7, a 47k and a 10 microfarad as our RC delay going to our offline. This is allowing us to get a measurement at this point because of that resistor. And it's measured with reference to ground. So if we look at my enormous penis, we look at the meter here. I'll put a battery across the inputs and we can see it drops down to 0. And if I reverse it, it drops down to 0. It's very hard to actually see on this meter properly and also get good connection on the battery this way, but that's the general idea. And if I test it on the other channel input, it drops to 0. Don't forget this is an auto-ranging meter, so it's going to constantly try and search in the millivolt range. But we can see that the input stage, if you want to call it that, is functioning, and we're getting, well, with respect to Earth, a 0 volt on this meter, which is actually with reference to the negative rail, the negative voltage rail, which is at currently 20 volt. So we need to move on to the next stage, which is, in this case, the relay driver. Okay, so this is our basic relay driver, and if you're going to have multiple relays, I would strongly suggest having multiple circuits of this. Now, this is just a standard silicon diode, like a 1N, 4001, 4007, whatever. This is a 12 volt relay with a 254 ohm approximately coil, and it's one of these Omron clones. So this is a relay I'm going to be using in the demonstration. Basically, you just look at the specs of this relay or whatever relay you're using to make these calculations. Now, the emitter resistor here is calculated the same as it's always been calculated in most of my videos. Is we take the VCC, which is the voltage on the positive rail. At the moment it's 20 volt. The final design will be anywhere close to 30 to 45 volts, so these values will have to change, therefore your resistor value is going to be different as well. But for the sake of demonstration, we're at 20 volt, so we need to know what the current draw of that relay is without having to look up its specs, which is what I2 is. So the formula is VCC take V2, which is the coil voltage, divided by the current of the coil, or the relay I should say. So V2 is 12, R2 is 254 as I said. I2 is calculated by dividing V2 by R2, which gives us around 47 mA. So the calculation of R is now 20 volts minus 12 volts, which gives us 8, divided by 47 mA, which gives us 180 R. And I would use probably a 1 watt resistor there. However, in this test I'm going to be using a half watt metal film resistor, which will do for the test. So next stage is to build this little circuit up and see if it works. Now, this single drive transistor may in the end change to a Darlington transistor. Not too sure yet, but let's build it up, connect it all up to the offline, and you can imagine the RC delay, the 47K and 100 microfarad capacitor is actually sitting at this point, not where it is on the circuit. But it's already in there, and it'll all make sense when it's finally drawn up as a complete schematic. Let's get going. Okay, after messing about and changing this low ESR 35 volt capacitor, which is starting to vent because it had too much reverse voltage applied to it, so I changed it to a 63 volt capacitor. We now have this circuit working with this circuit. Now this is the relay driver over here, and this is our original circuitry here. So if I turn the power switch on, you can hear a little click there. So if I now measure across the relay coil and we look at my enormous penis, we look at the voltage, we've got around 11 volt there. Now when it's not connected to the relay, we're getting close to 20 volt. That's only because the driver's not loaded down. So What I will do is I might connect up an extra set of fly leads here so we can see the voltmeter voltage. Okay, so we've got 11.2 there. Turn it off. It's almost instant off, which is okay. It won't be if it's connected across the filter caps of a power supply of the amplifier yet. Keep that in mind. So, and after about 3 seconds the relay engages. There's a slight secondary click, or first click in the relay there, and then a secondary one. Right, so now if we do the DC test, which is, adding DC to the input, relay drops out and takes an awful long time to reset. So I reckon it's because of this capacitor here. Yeah, this capacitor, this non-polarized one, is storing a charge. Because I just went to reconnect it, and there's actually only one end of the capacitor was touching the breadboard, and it reset. See, that's very interesting, that is. Now the capacitor's discharged, so I'll swap the polarity around on the input. There goes the relay. Of course, it is really supposed to discharge, and well, you would expect actually by the topology of these diodes here in the circuit that it would actually give the capacitor also a path to discharge to, but apparently not. Well, so there's not much I can do until that capacitor discharges, unless I just short it. And yeah. So we know that the DC detection is working, but it holds the thing in mute for quite a fair while until this capacitor discharges. The same would be true on this side, but that's okay. That's no real great issue. This is what electronics is all about, having shit everywhere. Now, I've, for shits and giggles, added a second relay driver, and I've also now changed it to a Darlington driver, because this single transistor on its own was getting quite hot. The load's up at the moment. So now we can see there's about 12.6 volt across each of these drivers. Well, it's only connected to one, but they're both the same. So if I just put my fingers on top of these transistors, they're not getting overly hot, but a single transistor was. Remember, one transistor is handling all the current. In this case, there's two transistors now sharing the current. And a Darlington also will increase the gain of the transistor if it was single. I haven't updated the schematic yet, but I will do shortly. What I was doing some preliminary testing. So, and this wouldn't be an Astro 30 video without blowing up a capacitor. Pity it didn't go off bang, but it was pretty close to going off bang. I could say that this is pretty much well now rooted. I'm not going to use it for anything. So just do the DC test again. Relays drop out. And I have no idea how long it's going to take for those relays to re-engage. So what I'll do is I'll stop the camera now. I'll let the circuit run. It's 1:48 now, so we'll see how long it actually takes for the relays to re-engage. Way too long. Also, those 100 microfarad capacitors are way too large. Takes an awful long time for the DC voltage present on the wires here to activate the circuit. So I've changed them to 10 microfarad electrolytics at 50 volt. The final design will use non-polarized. It shouldn't really make a difference, but the reaction time is a lot faster. Currently at 13 volt on the relays. about 1 second. So that's more satisfactory. So that's now working, and it's working on both channels. I'll add another channel later and we'll see how many channels we can add, but I'm only going to add 3. Now, so we've got the driver circuitry, we've got the detection circuitry, and all that's working great, and we've experimented. I also added 2 22K resistors across each capacitors, well, one 22K resistor across each of these capacitors to help it discharge it faster. It shouldn't affect the overall performance of the unit. So whilst I'm thinking of it, we'll change that 10 microfarad and we'll add a 22K there, just for reference, and I'll change it on all of them later. As for the relay driver, we're looking at a Darlington driver. Like that. So that's the change made to that, and nothing else has changed on that. So we really need to work on the next bit, which is the loss of AC detection, and voila, this is our loss of AC detection circuit. Basically all this really does is we look at the AC voltage coming off the secondary of the transformer here and slightly filter it. So we're looking at the negative going cycle mainly, which goes through this basically this voltage divider network here of these 215K resistors. This diode here comes off of the VCC line, which is the positive line, and it's only allowing the positive to flow that way. Because we've also got a negative voltage here, we don't want this to flow back into the VCC line. That's the reason why that diode is there. Normally when this is in operation, this transistor should technically be biased off. There should be no current flow coming through the emitter collector junction to the off pin. When we remove this negative potential here, well, this transistor is now going to be turned on via this circuit path, so it's going to be forward biased. Biasing this transistor on, allowing the earth to flow up to the off pin, and essentially making the relays drop out. That's one way of doing it. You could simplify that and have, you know, just a single diode going across the drive, positive drive for the relays. That would be a simpler circuit, but yeah, I'm going to do it this way. So we'll have a look at this. We're going to connect the VCC voltage to here, the negative voltage from the power supply to here, and see what that circuit does. So we've got that little circuit built up now, and I'm measuring from the open end of this 10 ohm resistor, which goes to the collector of that transistor, and with respect to the positive rail, and we're getting 21.7 volt, and that's without that diode connected to the negative rail, which is that diode on the left. So now if I connect this negative lead to that diode, we can see that it drops down to, well, less than 50, I'd say 50 millivolt. And of course, once we remove the wire, if I can, it comes straight back up to 21 volt. So now, if I connect the end of that 10 ohm resistor to the off point on our circuit, those relays should drop out. Okay, so I've got my wire stripped and ready to go, so I'll connect that to there. And this is our off point up here, and our relays disengage. The voltage disappears and my fly lead came flying off. So I'll reconnect that. Now, if I now reconnect this negative lead, the relays come back. So there is our loss of AC detection. We can imagine, even though it's currently DC, that this is the secondary of the transformer disappearing with the power switch turned off and coming back with it turned on. Can't quite get that wire to agree with me because it's bent. I can't find my pliers at the moment. Maybe I should have used a longer wire. Yeah, anyway, there you go. It switches back on and off. Back on. Disconnect it. Power goes away. Relays drop out. And of course the power supply capacitors would be discharging at this point. Hence the load is turned off. So I'll now reconnect the loss of AC detection wire. And there we go. The relays re-engage. So that's almost the circuit complete. How about having some form of indication when we are in protect mode? Well, I'll have to do a little bit of experimenting for that. And a little bit of experimentation later, I've come up with the simple circuit. We've got two NPN transistors, BC549s. This one's based through a 470k resistor is connected to the off pin, which is basically the relay drive part. That was the multimeter. This one is biased, base biased, forward biased off of the VCC line through this 10k resistor. So this transistor, when the relays are disengaged or it's in mute mode, this is biased on or turned on all the time, so that will illuminate the LED. So when this transistor is now biased on via that RC delay, that's basically where it's connecting. It's connecting between the 47k resistor and the 100 microfarad capacitor. So we're going to have a positive voltage here, so that's going to bias this transistor on, effectively shorting this base to ground. So essentially turning the LED off. That's when the relays are on. When the capacitor in the RC network is at 0 volt, this transistor is now off, and then therefore this transistor can then forward bias and turning the LED on. That's basically how that works. And as we can see, there's a little LED there on the circuit board not doing much. Now if I remove my loss of AC detection wire, the negative wire, the LED comes on. Now if I reconnect that wire, relays come on, the LED goes off. How simple is that? Now with this 22k resistor, which is for the LED here, this is also its value is also going to be dependent on the voltage supply rail. This is going across one half of it, so from the positive through to the 0 volt rail. So you'd have to calculate the resistor value for this LED, knowing what the current draw of that LED is, which, well, someone might know what the current draw of that LED is. I have no idea off the top of my head without looking it up. I think it's about 5 mA or something. Anyhow, you just use Ohm's law to calculate that, but just keep that in mind because I already blew up an LED having a 10k there at 20 volt. And yeah, killed it. Was wondering why it wasn't lighting up anymore. That could be the reason. Anyhow, that resistor in the relay circuit there, that's marked R, that should be higher than a 1 watt device because that is getting pretty warm. So I would probably use a 5 watt device there for each of your relays. Currently I've only got one running, and I'm using a 390 ohm 1 watt resistor, and the voltage is sitting close to where it should be, which is 27 volt, which gives me 12 volt across the relay. At 35 volt you're looking at more likely at 470 ohm to 680 ohm. Just use the little calculation there and you can work out what the resistance should be. And just to close out this video, I've now added a third detection channel, or third input, and you can have as many as you want, as I said. See, working fine. Brilliant. So as I said earlier, all I've done is I've changed that to a 10 microfarad and added a 22k resistor across that capacitor to act as a quick way of discharging it. But that shouldn't affect the filtering network that much, and everything else is pretty much the same. Anyway, I'm the Astro 30, and if you enjoyed this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying, I will see you in the next video. Bye for now.